Hi, this is Amir, and in this video I'm going to talk about our position paper that we sent to ICCV 25 explainability workshop. In the rest of this video we go over this agenda together. First we discuss what explainability is and why it matters. Then we state our research question and our focus in this position paper. After that we state our position about XAI research. Finally we touch upon the steps we have taken with this VU, and we talk about future work. So let's start from this question. What is explainability? The first thing is that unlike before machine learning era, we find solutions with optimization these days where we have loss functions defined for some patterns that are in gigantic amount of data, and we find the desired functions via optimization rather than an analytical study that takes years. Because we find solutions with analytical study, we don't know the mechanism the function takes to get us from input to output. So both input and output are human understandable, though the mechanism, because it is found with optimization, it is not necessarily human understandable. There are some works, for example, that show, segmentation maps, but if one thing to note is that if the segmentation map is inside in the model output, although the output is human understandable, again the mechanism could be not human understandable. And the last thing is that there is no consensus on what the definition of explanation is at the moment, and this is natural in humans. Like we accept something as an explanation, but defining it formally, mathematically, is very hard. In this position paper, we focus on attribution methods. These methods try to attribute a decision of the network to its input features and rank features based on how important they are for an outcome. One problem with attribution methods is that they tend to be very complex out of the box. If we use vanilla grad, which is the gradient of the network with respect to its input, and we realize that the gradient usually looks very noisy and complex. This is in contrast with humans' tendency to understand and accept simple explanations. So researchers in XAI have came up with different methods to simplify complex attributions and in general complex explanations. So because humans tend to understand the simpler explanations, one natural question is that how to reduce the complexity of these attributions. Also, what are the sources of this complexity? And if we are aiming to reduce this complexity, what trade-offs we should be making when simplifying these attributions? Now we want to state our position, but the way we want to do it is that we first go over one branch or one approach to attribution methods, to reducing the complexity of attribution methods, and then we pose two fundamental questions that helps us in deciding between post hoc and anti hoc, and then we iterate our positions. So let's first understand post hoc attributions together. The features that are important for us about attributions in this position paper is that usually, by definition, most of the post hoc methods come after training. Actually, the name post hoc comes from the fact that these methods are designed by assuming the network is fixed, so everything happens after training. Usually these methods are designed by two fundamental components. One is perturbation or stochasticity. This stochasticity can be in input or weights or architecture. And when you get several samples of attributions from different perturbations, you aggregate them. And we have shown in previous works that this aggregation and perturbation together create implicit low-pass filters, which I will describe in more detail later. A fundamental problem in post-hoc attribution methods, we think, is that the surrogates that are created by low-pass filtering or aggregation and perturbation become implicit by design. And because these surrogates are implicit, the surrogates are smoother, so the explanation becomes simpler. But because the surrogates are implicit, some of their properties, some of their important properties remains uncharacterized, like the drop in performance or how different the surrogate is from the original network. Now that we have discussed a little bit post hoc attribution methods, it's time to state our fundamental questions. The first fundamental question is that is the attribution complexity an artifact of the attribution method, explanation method that we have chosen, or the complexity originates from the complexity in network? The second fundamental question is that if this complexity comes from network, is this complexity absolutely necessary for the task we have at hand? The answer to the first question is, for post hoc methods, we believe should be that complexity is an artifact of attribution methods. So people who are doing complexity reduction of attribution must implicitly assume that the problem of complexity is an artifact of attribution methods, so it makes sense that I change the attribution methods to solve the problem. And the second question is that even if the complexity of attribution comes from the network, I need this complexity. So I cannot change the network, I cannot simplify the network, so I have to focus on changing the attribution method. And this position paper is about spectral view, or the promise of a spectral view. And we think that spectral view is useful, and this is the first immediate or early results of having such view, that we can unify post-hoc methods as low-pass filters. I will link to this paper that we have in eXCV 24 in the end of video. And so we can unify these post-hoc methods as having a gradient field and convolving it with a probability distribution. And the probability distribution, for simplicity, we assume this is in input space, but nothing stops us from assuming that this is on parameters. Of course, this becomes more complex when you put it on parameter space, but the gist of the method stays the same. So we have a vector field and we convolve it with some distribution. This is not exactly accurately describing post-hoc methods, but it is close enough to give us some intuition. If you want exact formulation, you should see or read the paper that I link at the end. And the general idea of that paper is that we have some functions. They are decomposed into several frequencies, and gradient operator amplifies high frequency informations proportional to their frequency. So if we have some high frequency information, they're going to be amplified, and the effect of this amplification makes the gradient field very jittery and noisy, and usually these high frequency informations dominate the explanation. To solve this problem, we convolve this vector field with probability distributions that are perturbations, and by sampling and aggregation, this is kind of approximating this convolution, and convolving a signal with a probability distribution is called low-pass filtering in spectral signal processing. So we can remove the effect of high frequency information if we do this low-pass filtering. So we can remove the complex part of the vector field. Another way to think about post-hoc methods is that we have a hypothesis space. Now we have in this slide we have a statistical learning theory viewpoint in which we have hypothesis spaces and things like that. So with ReLU activation function and vanilla grad, we have a hypothesis space of functions where vanilla grad acts noisy and complex. And to reduce this complexity, we project it, or let's say we approximate it with with a set of functions that are of less complexity. And the way we do this reduction of complexity is convolving it with some probability distribution. And the hypothesis space that is created is smaller because some sharp functions or some functions with sharp changes are going to be projected here, and that is the result of smooth grad. So the functions that are created, or the surrogate that is created implicitly by smooth grad, is belongs to a smaller hypothesis space that is the result of convolving ReLU functions, or the architectures or networks that have ReLU activation with some probability distribution. Now we are ready to discuss anti-hoc approaches. The most common theme in anti-hoc approaches is that they usually focus on things you can do before training, and they are usually designed by making modifications to the architecture instead of the explanation method. So they usually adopt a very simple explanation methods like vanilla grad or vanilla grad and some post-hoc approaches on top. But ideally we use a very simple explanation method like vanilla grad, and we try to think what we can do prior to explanation phase, in design phase, in modeling phase, before training, to make the function have a smooth gradient. The main challenge that we have in anti-hoc attribution methods is that when you make such changes, usually the function becomes very challenging to optimize, and it's very hard to explicitly know what sort of constraints we need for some properties in the gradient space. Like, we want the gradient to look not noisy. What kind of changes I need to make in my network architecture to achieve that goal? So let's go over the answers to the fundamental questions we had before. The answer to the first question, that is about the source of complexity, in this method should be that the complexity, or the people who do anti-hoc approaches, must implicitly assume that the source of complexity is in the network. If they assume that the source of complexity is in the attribution method, then it does make sense to do anti-hoc. Also, their second assumption is that although it is in the network, we don't need all the complexity to achieve some performance. So they make these two implicit assumptions to justify doing explainability anti-hoc, or reduction of complexity of attributions anti-hoc. So if we go back to our spectral view, one of the benefits that we had from spectral view was to unify post-hoc methods as low-pass filtering, and the second benefit that we can get is to show formally that network architecture is the source of complexity. So we can formalize some of the missing connections that we had before in explainability. In explainability, we used to assume that if you have a complex network, it naturally leads to a more complex attribution. But this relationship has never been formalized and theoretically justified. If we use this spectral view, we can show this. This is our ICCV paper that I also link in the end of this video. So if you go back to our view that we had a vector field, here it means we want to take the vector field as given. We don't want to convolve with some other perturbation distribution. To tell you a bit more about our ICCV paper, which has the same spectral viewpoint, in this paper we assume we look for the sharpest change that a function can make, and we realize that the sharpest change in the decision boundary of the function is somehow related to the activation function you choose. And if you choose ReLU activation, there are several sharp transitions in your decision boundaries, and those sharp transitions result in gradients that change sharply. On the other hand, when you use a smoother activation, which we achieve by smoothing ReLU activation, something like soft plus, if you use soft plus, then the resulting function is a function that has less sharp transitions, or the sharpest transitions of this function is smoother than the sharpest transitions of the ReLU function, or the ReLU network. And if you take the gradient of this guy, this looks a bit smoother. And we take the Fourier transform of such function, and we show that these tails are correlated with the spatial domain Fourier transform of the attribution. So if the tail is heavier in function space, it is also heavier in spatial domain of the attribution, which means you have a heavier tail in the attribution, which means you have a more complex attribution. To dig deeper in this, you need to watch the other video we have about complexity faithfulness of attribution methods. Now, if we go back to our intuition that comes from statistical learning theory, we had a hypothesis space, a big hypothesis space from ReLU, and we could do post hoc convolution with some perturbation distribution to reduce or to restrict this space to functions that have lower complexity. Also, there's another way we can do the same restriction, or we can do the same thing, which is restriction anti-hoc, which means we can take all these functions in a ReLU space, change the ReLU to some smoother function. In this case, it is soft plus. So we have a hypothesis space that is the result of using soft plus in the network, and the resulting functions have less sharp transitions, so you cannot model the whole space, you can model part of it. And the relationship between post hoc smoothing and anti-hoc smoothing could be, it is not characterized yet, so each of these could give you a function that is similar or the same thing. So to very quickly summarize our position in the paper, we provided two questions that allow us to uncover the hidden assumptions of post hoc and anti-hoc approaches, which concerns first the source of complexity in attribution and the necessity of complexity in the function. Now, to choose between post hoc and anti-hoc, we can answer these two questions in maybe other data modalities to choose between post hoc and anti-hoc. Also, we showed that spectral signal processing is a promising direction that helps us formalize some of the questions in explainability regardless of the chosen approach. Now let's go over future works together. The first thing is that no matter what you do, post hoc or anti-hoc, theory in XAI is missing. And most of the methods are doing kind of engineering and heuristic approaches. Now, if you make it specific to anti-hoc approaches, the first thing is that when you restrict the function space, like we did this activation function, changing activation function, there's no way of clearly formalizing it, or how it aligns with our aims and things that we want in explainability. So this requires more theory in anti-hoc approaches. If we do anti-hoc, then optimization reachability is another thing that needs more theory. So in anti-hoc approaches, usually we restrict the hypothesis space prior to training, and this makes training really hard. So there's no analysis basically that if we restrict the hypothesis space, how it interacts with gradient-based optimizers. Another thing is that what kind of inductive biases we enforce when we make the changes. This has not been formalized or studied yet. So let's say I want to reduce the complexity. Now I know that I can change the activation function. But there are many other components like max pooling, like batch normalization, like softmax. There are convolutional layers, there are dense layers, there are attention layers, things like that. And we don't know what kind of inductive bias we enforce when we want to restrict the space anti-hoc. Here, inductive bias does not mean the statistical learning theory meaning. Here it means inductive bias in the attribution domain. Like if we use dense layer instead of convolution layer, what do we expect in attribution map? And now some of the missing theories in post-hoc approaches is that if we know that post-hoc approaches are essentially low-pass filters, why don't we make it explicit and design explicit low-pass filters? If we know it is just low-pass filtering, why can't we extend it to other domains, like graphs, like wherever the Fourier transform is defined, like graphs or groups or something like that? And finally, because we know this is just low pass filtering, we can borrow several tools from spectral signal processing that are made for ranking or knowing how effective low pass filters are. Thank you for your attention. Please let me know if you have questions in the comments, or feel free to reach out via email.